So the question, as we just explained, is how do we handle more users? And we know that in order to do that, in order to handle more capacity, we need to be more efficient with our threads. We need a programming model that supports what we're trying to do. And so this is not a controversial idea. There's a lot of different ways to do this. But essentially, what we want to do is make our code a little bit more friendly, a little bit more generous. We want to be able to signal to other threads and other resources in the system that we're not using a given thread and that it's up for grabs. In order to do that, we need to be a little bit more aware of all the opportunities that we have to get off the thread, which means that we need to know when we have to be on a thread. What are some of the things that we can do that might monopolize a thread? Well, the Fibonacci series, right? Very classical progression in computer science will block a thread. It's something you have to do on the CPU. So you do it on a thread somewhere. It could be the main thread, but it's still a thread. What about cryptography, right? Bitcoin mining, these kinds of things are CPU intensive. There's no way to sort of not use the CPU for that. You're going to be on a thread somewhere doing that work. What about input and output? Well, no, we don't have to use Java I/O in input stream and output stream. And I'm not proposing this hypothetically either. This is not like a far-flung idea that might work in the next 5 years. Furthest thing from it. We've had on the JVM good support for asynchronous I/O for 17, 18 years, going on, more than that, right? We've had it since February of 2002, since Java 1.4. Java.nio.asterisk has been there since Java 1.4. So that support, whenever you're watching this, that support is already long since established. So the question then is, why don't we use it? Why, if that's a place where we're doing a lot of our work, if most JVMs on observation are actually just idle, they're just parked waiting for bytes to flow across the buffer, across the network, then why don't we use it, right? And why aren't things written in that way by default? And I would say there's a few reasons for this. First, people have a tendency to fall for the fallacies of distributed computing, right? They assume that data and the network is infinitely fast, that it'll never fail, that the next byte will surely just be right around the corner, and that once you have data flowing in, nothing's going to stop it. You'll get all of it, right? These things are not guaranteed by any stretch, and you can't afford to build software predicated on the assumption that they are going to be here. So that's part one. And the other thing I would say is that using Java NIO is not easy. It's not natural. And it's not going to give you more than Java I/O input stream and output stream. That is to say, with Java NIO, you can send bytes across the wire or into a file, and with Java I/O, you can do the same thing. So for a lot of people, if you've learned one, you don't necessarily see the need for the other. So that's two reasons. The third reason I would say is that we don't work at that level. Most of us don't use Java I/O input streams for our day-to-day code. We don't write code at that level. We write code in terms of higher order computational metaphors, abstractions that allow us to describe asynchronous streams of data that will come and that will resolve eventually, but that isn't here yet. And so we need some way to model asynchronous, potentially unbounded streams of data. We need some way to say that when that data arrives, that we can handle it gracefully. We can process it. We can handle errors. We can deal with disconnects. We can deal with all that kind of stuff. The Java I/O input stream and output stream interfaces, while greatly simplifying and while very enabling and very powerful, don't give us that, right? They give us this very simplistic view of the network, and that hides things that we should really try to be more aware of. So what can we do? Well, there have been a number of different organizations that have tried to create APIs that allow us to describe asynchronous sort of computational processing, right? Asynchronous multi-threaded processing. And a number of these different organizations got together starting in 2015. These organizations include, but are not limited to, Lightbend. At the time it was called TypeSafe. It includes Netflix. It includes Pivotal, of course. The Spring team is at Pivotal, Project Reactor. And includes the Eclipse Foundation. So these different organizations got together in 2015, and we extracted out 4 very, very simple interfaces. These interfaces are part of the Reactive Streams sort of specification. It's a de facto specification that describes 4 very simple types that all these different major players in the reactive ecosystem space agreed to use to describe asynchronous, unbounded streams of data. Then we added, a lot of support around that, right? We said these are very, very basic types. These types are sufficient in describing a thing that will eventually resolve into data. You might think of them as sort of discontiguous Java arrays, okay? They're very, very useful, but they're not useful enough. And we're going to see in a moment that what you really want is something that sits on top of that interops with that specification, but that gives you power on top of that. But before we do that, let's take a moment to talk about reactive streams itself. Okay, so the reactive stream specification, you can find reactive-streams.org, and there you're going to find information about, the motivations, how it works, the current versions, the TCK, etc. One thing that's kind of interesting is that the interfaces here have actually become kind of ubiquitous, right? They're so ubiquitous that other languages have adopted them in their own way, of course. And indeed, even in the JVM, you have in Java 9, which is as of this recording, more than 2 years old already. As of Java 9, you have Java Util Concurrent Flow. So that's a top-level type that has within it the 4 types I've referenced or alluded to earlier. So you have Java Util Concurrent Flow.Publisher, Flow.Subscriber, Flow.Subscription, and Flow.Processor. So these types are now interchangeable. You have the reactive streams types, and you have the mirror interfaces in Java Util Concurrent Flow. You can adapt one from the other. And in fact, now, the reactive stream specification, the implementation, the API that you get when you use the jar, includes a 5th type, which isn't an interface. It's actually a concrete class that gives you converters from Java Util Concurrent Flow.Publisher to reactive streams, org.reactivestreams.publisher. Okay, so the reactive streams specification is very useful. It's foundational. It's even part of the JDK now. Okay, so everything that we're going to talk about today assumes the presence of either the reactive streams APIs, which depend only on Java 8, or the Java 9 Flow reactive streams types, in which case you need Java 9.